Hi, this is Class Notes D in Lesson 2, and this Class Notes asks us to solve the separable Foden definition 2.2.1. And really quickly here, this should be 2.2.2, so I fixed that in the lesson notes that do not have these annotations. But the point was to go back to this definition and solve this ODE, which is the Logistic ODE. So we are going to do that in this class notes, and we are also going to apply the initial condition over here, p of 0 equals p sub 0, and verify that this is the solution that we get. So let's go back to the ODE itself and start there. So the logistic ODE is dp dt equals ap minus bp squared. It won't matter too much for us, although it will come up at some point that the parameters here, a and b, are positive, but I just want to mention that so that we are clear that they can't be just any old number. They should be positive. So this is an ODE that is first order, but it is not linear because of this p squared. So thus far in this lesson, all that we've studied are separable ODEs. So hopefully this is separable. And indeed it is, but it's not so clear perhaps that it's separable, because what we have to do, again, if we take this shortcut, the quick way to solve this, like we talked about in the first class notes in this lesson, what we have to do is separate the variables here, and we get all the p's on one side, all the t's on the other. And on the right hand side, I should say, that antiderivative is pretty straightforward. We are left, though, thinking about what to do here on the left hand side. So this is one of those instances where if you try use substitution, won't work out. The integration by parts integration technique is also not going to work out. And the reason is that what we have to do is partial fractions. So needs partial fractions. All right, needs partial fractions. And let me fast forward a little bit to the end of the lesson notes where the practice problems start. So you can see right up here that I have included some links for partial fractions review and also some problems in case you want to solve those. These links take you to Paul's online notes, which is a great site to review these type of concepts. So what I'm going to do here is just remind you very quickly how partial fractions works, and then apply it to this integral on the left here. So we'll say quick partial fractions review. And I'm going to keep the review as simple as possible in the sense that I'm only going to remind you of the bare minimum that we need to solve this problem. So let's change the problem a little bit to make it a bit more concrete. In the integral that we are trying to do up here, right, there are unknown parameters, and I just realized that I forgot the b down here. Let's put it up there, put it in there again, a b minus, oops, wow, I really made a few errors here, also up here. So let's put this AP minus BP squared, AP minus BP squared. So anyway, in here, there are parameters that are unknown, A and B. And let me simplify things a little bit, make the problem more concrete so we can remember how partial fractions works. So let's try to integrate x squared plus 5x plus 6 in the denominator and use partial fractions to break this up. So what do? In partial fractions, we say, let's look at the integrand, and if the denominator factors into hopefully linear factors or quadratic factors, it's a little bit more complicated if we have anything higher than that. But again, we're just looking at the bare minimum here. This denominator factors into these linear factors, x plus 2 and x plus 3. And what we want to do now is we want to say this equals something divided by x plus 2 plus something else divided by x plus 3. And now to figure out what a and b are, they're going to be some unknown numbers, and we'll figure them out in a minute. We are going to multiply all sides of this equation by the denominator. So I'm going to multiply by x squared plus 5, let me move this over actually, make it a little easier, multiply by x squared plus 5x plus 6, the entire equation. So on the left-hand side, this would cancel out with that, and I would be left with just the numerator here. So 1 equals, and then on the right-hand side here, because x squared plus 5x plus 6 factors into this, right? Then this is like multiplying by x plus 2 times x plus 3. That's useful because when I multiply this times this terms, the x plus 2's would cancel, and I would be left just with the x plus 3 times a. Notice that that's the same as if we just cross multiply these two. So taking that shortcut, we would then, the second term, cross multiply here to get the b times x plus 2 term. Okay, and at this point, you might remember learning how to do this in Calculus 1 to solve for capital A, capital B. There are two routes. You can try to get all the powers of x to be the same and then set up a system of equations. For example, 3a plus 2b are the only numbers on the right-hand side. The only number on the left-hand side is 1. So one of these equations would be 3a plus 2b equals 1. Okay, and then you can derive another equation by comparing the powers of x. I'm not going to do that because that will throw us into solving a system of equations, and then we have to review that as well, right? And that also generally takes a long time. So I'm going to take the shorter route. I'm going to say, you know what? We want this equation to be true for all values of x. So I'm going to pick some very make judicious choices for x here. I'm going to choose x equals -2. So if I choose x equals -2, the left-hand side stays 1. Over here, it'd be 3 minus 2 would just be 1, so I'd have 1a. And then x plus 2, hey, this term is 0. So that is really nice because look what's happened. We have quote-unquote solved for a equals 1. You might be thinking, wow, that was so simple, and I totally agree. So we'll do it all over again. This time, though, we're going to choose the x value that makes this term 0 because we want to solve for b. We're going to choose x equals -3. The left-hand side stays 1. This term becomes 0 because x is -3, and this term becomes -3 plus 2 is -1b. Great, and that is not quite as simple as the a value, but pretty close. We just multiply by -1, and we have the b value. So therefore, 1 over x squared plus 5x plus 6 equals this a value, 1 over x plus 2. Remember, the a went with the x plus 2. Okay, plus b, but b is -1, so -1 divided by the b went with the x plus 3. X plus 3. And you could check this, right? You could, if you wanted to, take a minute and combine this right-hand side and multiply everything out just to make sure that we did all the math correctly. And I would say, so if I go back to the original example that I'm saying here, we integrate 1 over x squared plus 5x plus 6. I can now split that up into these two integrals. And this is really the utility of partial fractions, right? I did not know how to do that integral before, and now this and this are two integrals that you might recognize in terms of the natural log. So they're a small u substitution away from being natural log of x plus 2 minus natural log of x plus 3 plus c. And because when you subtract natural logs, they become quotients, this would be natural log of x plus 2 divided by x plus 3 plus c. So again, there was an integral we did not know how to do. We did a partial fractions technique, all of this stuff over here, and then we were able to split it up into integrals that we indeed could do. So that is a very quick review of partial fractions. Again, follow the links that I suggest in the practice problems to get a more thorough review. But this is all that we will need to go back to the problem at hand, right? Returning to the ODE, we wanted to integrate this. So I'm going to go down here on the next page, and start that up again. Actually, there is no next page. So I'm going to scroll down a little bit here and put it, I did leave some room down here. So I'm going to say on this page, so I'm going to say in red, continuing class notes D. Okay, so we were trying to integrate AP minus BP squared. So we're going to do the same partial fractions approach here. We will try to break up this AP minus BP squared. And let's see how we can do that. So the denominator, I can factor out a P and I get A minus BP. And similar to what we did before, I'm going to put each one of these linear factors in the denominator in its own fraction. And I'm going to put a numerator of A and capital B. So now I'm left trying to figure out what the unknowns A and B are, capital A, capital B, in this equation. And as I did before, I'm going to multiply both sides by the denominator. And I'll just factor it here to make it easier. And as we saw before, this part on the left-hand side just gives us the numerator, which in this case is still 1. And then on the right-hand side, we just cross-multiply. So we get A times little a minus BP plus B times P. Okay, and then choosing again some very well-chosen values for A and B. We'll move this over. We can choose, in this case, P equals 0. P equals 0. So if we do that, this term goes away, and this term goes away, and we just get capital A little a equals 1. So 1 equals capital A little a, implies A equals 1 over A. I had mentioned earlier that we were going to make use of the restrictions on little a and little b at some point. This is one of these examples, right? We require that little a is positive in the logistic equation. So that really helps us out because we can divide by it here. And then going back here, we want to make the other choice for p that makes this 0. So if I set this equal to 0 and solve for p, I will get p equals a over b. So I'm going to choose that. If I plug it back into this equation, then the term with capital A is going to be 0, and then I just have this left over with replaced by little a over little b. And then I am trying to solve for capital B. So I go back here and I multiply by little b, divide by little a, and I get capital B equals b over little a. Okay, great. So I'm in a good position here. And I now can put these capital A and capital B values back in here and conclude that if I'm integrating 1 over AP minus BP squared, that is the same as integrating capital A, which is 1 over A times 1 over P, plus dP, plus capital B, which is B over A times 1 over A minus BP. Okay, great. So at this point, we can do one of these integrals pretty quickly. The first one here. So this is the antiderivative of 1 over P dP. That is just ln of absolute value of P. And it's being multiplied by 1 over A. So there we go. This one takes a little bit more work, but I'm going to write down what the integral is and then kind of figure it out backwards just to illustrate how you would avoid the u substitution. Okay, so let's say that someone tells you that, hey, this is the integral of this integral on the left-hand side. This is what you get when you integrate it. We would say, well, let me double check that, right? Let me see, if I differentiate this, what would I get? I would get 1 over A minus BP. We have that here, great. But then I would multiply by the derivative of the denominator, which is negative B by the chain rule. Okay, and that negative B is not in here anywhere. Okay, so this is sort of a quick way to realize that this ln of a minus bp is not all there is to the integral. I have to divide it by negative b. Okay? Because if I differentiate ln of absolute value of a minus bp, I get 1 over a minus bp. Great. But then I have to multiply by negative b. So by dividing by negative b, I make sure that indeed I'm integrating this thing which does not have a negative b. All right, so plus c. And then now we keep simplifying here. So we have this b, negative b, they cancel because b is not 0. So we have 1 over a ln of absolute value of p minus 1 over a ln of a minus bp. Great. And at this point, we can see that we can factor out the 1 over a, and then I can combine ln of p over a minus bp plus c. So we have now finished the integral that was the tricky one from the very beginning of this ODE. And we've determined that that integral looks like this. And we can then link it up with what we had with the right-hand side when we first started doing this. So I'm going to scroll up so I can remind you what that was. So here we were. We just finished doing this integral, and we already had determined that the right-hand side was t plus c. So I'm going to go back down to where we were just a minute ago and put in that t plus c, and oops, and finish off the solution. Great, t plus c. All right, so I'm going to multiply by little a plus, I'm going to introduce a new constant here, d, because it's just capital C times a. And then I'm going to exponentiate. So I will have p over a minus bp equals k e to the at. So I've done our usual thing here. You know, when I exponentiate e to the d, I've called that k, just to not have so many constants floating around. They're exponentiated and multiplied. Okay, and then at this point, we want to do some algebra to solve for p. To do that, I am going to multiply both sides by a minus bp. And then I'm going to distribute ak e to the at minus bpk e to the at. And then I will combine the p terms, p plus bpk e to the at equals ak e to the at. And then I will factor the p. And then we will divide by this term, 1 plus bk e to the at. Great, so, and this is of course p of t. So we've gotten to a solution. Let me go back now to C and compare that to the solution that we had at the very beginning. And one thing you'll notice here is that, first of all, we've yet to apply the initial condition, so we'll talk about that in a minute. But another thing you'll notice is that the numerator doesn't have any exponentials in it, and the denominator has e to the negative a. So that's kind of a clue that actually what we want to do down here with the solution we have is we want to divide both sides, numerator and denominator, by e to the at. So if I do that, then the numerator just becomes ak. 1 over e to the at is just e to the minus at. And the bk e to the at term, that becomes just plus bk. All right, so this is starting to look a little more like what is given in the solution above, and I'm just going to rearrange, swap the order of these terms here so that it looks even more like that. Great, so we're getting there. So now we want to apply our initial condition. So we're going to say p sub 0 equals p of 0, and then I'm going to plug in 0. This is the only place where t is, so that's just going to give us e to the 0, that's 1. So ak over bk plus 1. All right, so at this point, I want to solve for k. So very similar kind of algebra manipulation. So multiply by bk plus 1 on both sides, p0. Multiply this out, bk p0 plus p0. Combine all the k's on one side. So we're going to do ak minus bk p0 equals p0. Factor out a k, because remember we're trying to solve for k here. And then divide here. All right, so I'm not going to worry too much about whether this denominator is 0 or not, and we will see why in the next class notes when we talk about the limiting behavior of the solution. We'll see that actually a over b is the limiting behavior of the solution. So I'm going to take this k and then insert it back in here. And we're going to get something that is a little convoluted, but we will work through the algebra. So insert it in there, and we get p of t. Oops. P of t equals a times p0 minus a minus bp0 divided by b times p0 a minus bp0 plus e to the minus at. Okay, so this looks really busy, right? But what I'm going to do now is I'm going to multiply the numerator and denominator by a minus bp0. Okay, so in the numerator, that's going to get rid of this. So that's going to get rid of that. And we will say numerator just leaves us with a p0, which should start to look familiar. The denominator, when I multiply that into the denominator as well, that will get rid of this in this term. So that gives us the bp0. And then it'll add the a minus bp0 factor to e to the minus at. Okay, and that actually matches what we saw at the very beginning of this problem. So let me just scroll up where we started solving over here. So there it is. So there's the bp0, a minus bp0 with the exponential. And then we scroll down to where we just were. And there it is down there. AP0, P0, and the other part with the exponential. Okay, so that does it for this class notes. And scrolling back up to where we started, pointing out just a quick few things here, mostly as review. So again, this is fixed in the lesson notes that I uploaded without the annotations. We are in fact solving definition 2.2.2 for the logistic equation ODE. And then, as I mentioned, solving this involved partial fractions down here, and then involved quite a bit of algebra to not only solve for P of t and also to apply the initial condition. So all of that combines to explain the reason why there's a star on this problem. And then final thing to reiterate again, we did use partial fractions here. I only reviewed what was absolutely necessary to help us solve the problem, but there is a much more thorough review of partial fractions if you go to these two links that will take you to Paul's online notes. Okay, thank you.